like to thank the organizers and also Claire for inviting me. I mean, I'm very happy to be part of this wonderful and well-deserved prize. So I will talk about some joint work with GLU. And let me introduce some notation. So I will consider a smooth projective variety X, complex, and from time to time I need the dimension, so the dimension will always be n. I will denote by T star X the cotangent bundle of X, and I will also use this projectification, which will be P T star X, projective cotangent bundle. I use a naive notation. I mean, this is really a sense of differential geometry. And the main character of the talk will be the algebra, which I will denote by S of X. This will be the sum of the symmetric power of the tangent bundle. And this is also the ring of regular functions on T star X. And you can also see them in this way as the graded ring associated to the tautological bundle on this. So this is sum of H naught P T star X O P of 1. I'm sorry, of P. And now I should say that this is for P. Yeah, okay. Here also. Maybe I should put P. I think this, I would like to show you that this ring is a very interesting invariant of a smooth projective variety. It's very difficult to compute. I mean, a large part of the talk will be just to give examples, the few examples where we are able to compute this. And the second part will be a theorem with the GLU, to how to bound somehow this ring, in particular its Krull dimension. But let me start with example, and let me start with the simplest possible example, the projective space. So 1, what is S of P of V? Well, here is the answer. This is the direct sum of the symmetric algebra of PV star modulo the ideal generated by one element, which I call I. What is I is in V tensor V star. So it's an element of degree 1 here, which, of course, is canonically isomorphic to the endomorphism of V. And Y corresponds to the identity of V. So you see already for projective space, the answer is not trivial. I mean, it's an easy exercise. I will show you why this is true, but this is already somehow complicated. And what is the reason? Is that because this projective cotangent bundle here, P, so P T star P of V, what is this? Well, this can be identified canonically to the incidence correspondence. Maybe I will not call it, maybe Z, in P of V times P of V star. And Z consists of pairs of a point here, a hyperplane here, such as the point is this hyperplane. So from this, I mean, you see that this here is exactly the graded algebra which appears here. And then this hypersurface here is defined by this guy here. So from this, you get easily the result. But yeah, again, my point is to show you that this is already non-trivial in such a simple case. So let's take the next simplest possible example. I guess if I ask you to vote, the quadric would win. So quadric. So again, let's take like a smooth quadric Q in P of V, which will be defined by a quadratic form Q from S to V to C, non-degenerate, I mean, everything nice. And what is the proposition? The symmetric algebra of Q, I should explain something. What is S of Q? Let me take the Grassmannian G2V of two planes in this space V, 2V, and this embeds by the Plucker embedding into P of wedge 2V. And then S of Q, the answer is, so what is it? You get the symmetric algebra of, if you prefer the algebra of polynomials on wedge 2V. So maybe I will write this like this, polynomial or symmetric algebra of the dual polynomial of wedge 2V, mod something. Something is the ideal of the Grassmannian, IG2V. So if you prefer, we take the homogeneous graded algebra of the Grassmannian embedded in here, plus something, wedge 2Q. What is this? You know, we have Q here. We can view Q as a polynomial on V. Taking wedge 2Q gives a polynomial on here on wedge 2V, and this is what you get. Maybe I can give a brief sketch of how you get hints, say, how you prove this. What is, again, this rests on a geometric interpretation of this projective cotangent bundle. You can see it as a space of pairs, something in Q, of course, X, and some P. X is in Q. And P is a hyperplane in the projective tangent space to Q. So this is X in P in, how do you say, PTX or PTXQ. So I see this really in P of V. I see this geometrically. I have my quadric in a projective space. I consider the projective tangent space, which is a hyperplane in P of V. And then I take a hyperplane here. So this let's see, the dimension V should be of dimension P of V is of dimension n plus 2. Maybe I should put V n plus 2. So this is of dimension n plus 1. The quadric is the dimension n. So here again, this is of dimension n, and this is of Pn minus 1. Because there are hyperplanes in the projective tangent space. And given this, I mean, it's quite natural to consider a kind of Gauss map, gamma, from this, P star Q, to the Grassmannian of, let's see, this is a Pn minus 1, so it corresponds to an n-dimensional vector space, so this is Gn V, which is then V as a non-degenerate bilinear form, so this is canonically isomorphic to G2V. And so this one is XP. You associate just this and corresponding vector space here, P. And what is this? I mean, again, it's an exercise, so I will not spend too much time on that. The image is that the set of Pn minus 1 which are tangent to Q somewhere. So image T in G2V. It's a hypersurface, and it's not difficult to show that it's given by this wedge 2Q. So this is a zero set of wedge 2Q. And what is the fiber here? For a general Pn minus 1, there is just one point of the quadric where this is tangent. But for some points, you have a line. And in fact, this is exactly a blow-up. This is a blowing up of some T prime in T. T prime is the locus of n-1 projective planes, which are tangent to Q along a line. And the last step is to show that gamma star of O of 1, or G of 1, this gives the O of P of V, which gives the Plucker-Ambedi, P of wedge 2V. Of 1 is exactly the tautological line bundle here. From this, you see that the sections of the powers of this are the same than the sections of the power here, and then you get from this the equality. But you see again, I think it's interesting to see that even for something very simple like that, the answer is somehow maybe not complicated, but non-trivial. Okay, let's continue with, we had one quadric, so now let's consider two quadrics. X, Q1, Q2, so that will be in Pn plus 2. I want always my variety to be of dimension n. Let me assume n at least 2. In the case of curves, I have an elliptic curve. This is essentially trivial. And here there is a theorem. So it's due to many people. Antoine Etes, Andreas Höring, J. Liu, Claire Voisin, and myself. First of all, the answer, what is S of X? Well, you may expect something very complicated, knowing what it is for for one quadric? Well, it turns out to be very simple. It's a polynomial algebra in n variables with, I should say what it is as a graded algebra. Maybe I didn't mention that, but obviously, by definition, this S of x is a graded algebra, and here the degree of each xi is 2. Meaning that there is nothing in odd degree. The h naught of SPTX is 0 for p odd, and then it's a polynomial in what appears in degree 2. But that's not all. Let me recall that this T star x here is a, maybe I should add this, is a symplectic manifold. This is well known from people in classical mechanics. There is a canonical symplectic form on T star x. And then, you see, when you have a polynomial maps like that, I mean, you wonder what is, a polynomial algebra like that. I mean, you wonder what is the map from x to Cn given by the xi. And then this is, I claim that this is a Lagrangian fibration. You see x as, this is T star x. Right, this is the algebra function. This S of x is the algebra function on T star x. So we have naturally n function which appear with give a map like this. And this of dimension 2n, this is Cn. And the fibers are Lagrangian for this symplectic structure. And moreover, at least for here I have to assume that x is general, sufficiently general in the quadrics here. The general fiber, or I should maybe give a name to this. This is phi minus 1. Sorry, now for lambda general, what is the general fiber? Phi minus 1 of lambda is an abelian variety, A minus something of codimension that is 2. So this is what is called an algebraically completely integrable system, something which was very popular in the, let's say, in the around 1980 with people like Kähler and von Morbeck. This is something which appears in classical mechanics. This is quite exceptional when you have a mechanical system and you have such properties here. You can actually solve the mechanical system using theta functions. And this is something very rare and interesting. I mean, there are a few classical examples due to Jacobi and Kovalevska and people like that. And curiously, in this case, we get this situation. I should say that the proof is quite involved. I mean, it's not at all, it's not an exercise like the first two cases. It's really, I would say, difficult. And a bit surprising. I mean, I still don't understand very well why in this particular case, we get such a nice situation. There is other example of this kind of where this holds, and this is a Hitchin fibration. In fact, this to my knowledge, this is the only cases known up to now. I mean, so this would be example 4, Hitchin vibration. Let me recall briefly what this is. We take a moduli, we take a curve C, curve of genus G at least 2, and we fix integers R, D, coprime, and we look at the moduli space M, this moduli space of stable vector bundles of rank R et degree D. This is a smooth projective variety because of this hypothesis here. And now Hitchin defined something like this. So let's see. Maybe I should first define the, recall how you define the Hitchin vibration. You look at the cotangent space, T star M. And what is T star M at a point E, corresponding to a vector bundle like that? This is canonically isomorphic to H naught of C, and the endomorphism sheaf of E tensor with a canonical bundle. This is by third duality. I mean, maybe I should have started with TEM, which is just H1 of end of E, and then third duality allows to identify the dual with this vector space here. So these are endomorphism, essentially, twisted. And then when you have something like that, you can associate to U the coefficients of its characteristic polynomial, which you can write like, let's say, AI of U. This will be the trace of the wedge product, wedge I of U. See, wedge I of U will be an endomorphism of wedge I of E, and you take the trace. Now, because of the K here, this is not a scalar, but this is this length in H naught of C, Kc to the I. And then you take the collection of all these coefficients. So phi T star M goes to a vector space, it's a W, which is a direct sum of H naught C K I C. So I should go from 1 to the rank. Let me write this here. And then the theorem, essentially due to Hitchin, is that we have the same situation as here, namely phi, let's say phi upper star, which goes from the function, the polynomials on W, regular functions on W, so they're just polynomial on W, to S of W is an isomorphism. And 2 and 3 hold. So see again, an algebraically completely integrable system in this sense. And as I said, I mean, these are the only cases I know where this occurs. There is a last example that I like. I think I have some time to explain it. Up to now, all these examples are sort of stable under deformation. I mean, you get the same kind of algebra when you deform the variety. This is not always the case, and I would like to show that in the last example. So this is a rather simple example. The X will be a ruled surface. Namely, I'll take, again, C of genus at least 2. I take a rank 2 vector bundle, stable, and with trivial determinant. And I consider X P C of E. Then the proposition is that S of X is the direct sum of the H0 C S2P E, the even symmetric powers of vector bundle. See, actually, your lemma is not very difficult. Let me just give the idea. Tx, let's say, we have the relative tangent bundle here, which embeds into Tx. But this relative tangent bundle is just O x of 2. I mean, O of 1 is the tautological line bundle on this projective bundle. I just take its square. This is a sort of inverse of the classical formula for the canonical bundle, or the relative canonical bundle. Because this hypothesis, I mean, there is nothing coming from the base, I have just this O of 2. So now you see that the symmetric power, if I take the symmetric SP of this embeds OX, the section of OX of 2P, that just exactly this S2P. That's it, H0 C S2P E. This goes into H0 SPTX. And now we use some exact sequences to show that this is actually an isomorphism. There is something to prove, but it's not very difficult. Okay, so what are the consequences of this? First case, if E is general in the moduli space of this implies that S of X is just trivial, it's just the constant. This is because for E general, this S2P of E is stable. This follows from Narasimhan's shadowy description of stable vector bundles. And the stable vector bundles with trivial determinant has no sections. So this is not very interesting in that case. But there is a more interesting case if we take a vector bundles which becomes trivial on a finite covering. To be precise, let's take any subgroup of SU2C which acts irreducibly on C2. So there is a well-known list of such subgroups because it corresponds to a polyhedra in R3. And now take any surjective mass from pi 1 of C to G. And this defines a vector bundle E, which has the properties that I need. It's stable and with rank 2 and trivial determinant. And what is, in that case, H naught SP2E? Well, it's easy to see that S of X is just the direct sum. I mean, let's say the symmetric algebra of C2 invariant under the action of G. And of course, this is also, if you prefer, the algebra of functions of the quotient, C2 over G. This is something which is well known since Felix Klein. We have a nice equation. This is something of the form, for instance, if you take for G the double covering, what is called the binary icosahedral group, this double covering of A5. A5 is contained in SO3, and you take the inverse image in SU2, and you get, for instance, S of X is C of X, Y, Z mod X2, X squared, X2 plus Y, sorry, plus Y cube plus Z5. And so, I mean, these are. So you get a nice algebra for your S2. Last thing I should say is that, so I was with example 5, so 6. I mean, quite often this algebra is trivial, of course. Let me at least quote the cases which are known. S of X is C if X is a Calabi, I mean, that's trivial Schoen class. And, I mean, of course, it's not true for abelian varieties, so I have to say pi 1 of X finite. 2, X of general type. I think it's due to a ring paternel. I think the case where K example follows from Yau's theorem, but general type is more subtle. And the third case, which was a little surprising for me, is that if you take a hypersurface, X, so in Pn plus 1, let's say of degree at least 3, then again S of X is trivial. And I mean, I should avoid the stupid case of the cubic, plane cubic, so let's say N at least 3, at least 2. I mean, except, so N equal 1, degree 3. And again, this is due to Rig, Liu, Shao. But I should say it rests on computation in the 70s by Bruckmann and I think it's Rackwitz on symmetric differentials, sort of reduced to the case of symmetric differentials, which is much easier to compute. So you see, this shows that this is a very subtle invariant. If you think just of surfaces for 2, for del Pezzo of degree 4, take just n equal 2 here, you get polynomial algebra in 2 variables, And for the cubic, which is very close to which is that piezo surface of degree 3, you get 0. So it's a very subtle invariant. So these are about all cases in which I'm able to precisely describe this algebra. But so since we cannot do that in general, we can try at least to give some kind of bound of the size of this algebra. And I mean, a natural candidate to give bounds, it will take its dimension as a ring, its cool dimension. And so maybe I can state here a theorem. Dimension of S of x is bounded by the dimension of x, so I call it n, minus the Kähler dimension of x. So it's bounded by the Kähler codimension of x. And moreover, we know exactly the case of equality. If we have equality exactly when there is an étale cover of something of the form a times y to x. So this is étale cover. A is abelian, and y is of general type. So you see, this is a bit surprising because, I mean, these two invariants have not much to do a priori. I mean, here we are talking about symmetric powers of the tangent bundle. Here we are talking about multiples of the canonical bundles. There is no obvious relation between these. Still, we have this property. So maybe I should discuss first what is this Kähler dimension. Okay, maybe I should say from now I will, so here are the cases, the known cases where the algebra is trivial. So let me assume from now on okay, S of x is non-trivial. Minus is plus. No, yeah, okay. Well, let me explain first what is this dimension geometrically. Well, sort of well-known fact is that the dimension of S of x, and here I'm assuming that this is why I put this. Now this is 1 plus what is called the Ithaca dimension of O P T star x of 1. What is the Ithaca dimension for a line bundle, kappa of L? You take all this is the maximum of the dimension of the image of the, say we have a line bundle L on some smooth projective variety Y of the map from Y, the rational map from Y to some projective space defined by the linear system L to the K. So maximum over K. It's exactly like the Kähler dimension. I mean, if L was a canonical bundle, that would be the definition of the Kähler dimension. But you can do that for any line bundle. You look at the map defined by this linear system, and you take the maximum dimension of the image. In particular, this implies, you see that, so I exclude this, so this dimension is certain between 1 and 2n. This p test star x has the dimension 2n minus 1, so this is between 1 and 2n. The case, I guess I have not said that this algebra S of x has been very little studied, I think, in the literature. I mean, I tried to do a search on the internet, but it's very few mentioned. One thing which has been studied is a case where we have equality. So let me say just 2 words. Dim S of x is maximal, so it's 2n. By definition, this means that not by definition, by the proposition, this means that the Ithaka dimension of O of 1 is maximal. This means that this O of 1 is big. It's the maximum possible of section. And by definition, this means that T star x, sorry, Tx, tangent bundle Tx is big. And now this has been studied by a number of people, and this is the case occurs when X is a toric variety, for instance, of a toric manifold, also homogeneous. And there are some other examples in the literature where this is big. So our theorem goes somehow, you see that as soon as the Kähler dimension is non-minus infinity, we have a bound by n, which goes from 2n to n. Okay. Okay, I guess some time left. Ooh, not much. Yeah, maybe I will leave as an exercise to check that this is indeed, we have equality in these cases. For abelian variety, tangent bundle is trivial. This means that dim S of x is n, but kappa of x is 0. And for general type, I said that this is trivial. And so, again, we have just equality. And then it's easy to check that this conditions is stable under product. This is essentially Q-net formula under étal covering, finite covering. Okay, well, let me just give a very brief idea of the proof. It rests on I said we assume that S of x is non-trivial. That's one thing. And you can also assume, we assume, so idea of proof. We may assume that x is not uniruled. If it is, the Kähler dimension is minus infinity, and there is nothing to prove. In this situation, there is a deep result of Herring-Peternel. The tangent bundle splits into 2 parts, F plus G. F is polystable. Let me put this here. F is polystable with slope 0 with respect to pick up a polarization, but it will work with any polarization. Let's say we fix a polarization. G has negative slopes. G the Harder-Narasimhan filtration of G has a negative slope. This is not too surprising. We know that there is, again, a deep result of Miyaoka, which says that the slopes, if we take the Harder-Narasimhan filtration of Tx, the slopes are either 0 or negative. Usually you say that for omega 1, but then you just dualize. So there is, what we say is that the first part of the Harder-Narasimhan filtration splits somehow here. And now, to prove, so let's fix the rank. So this is the rank n. So this will, let's say this is of rank r, and this rank n minus r. And when we want to prove is that here the dimension S of x is S, and here kappa of x. So somehow this part controls the dimension of the symmetric algebra, and this part controls the Kähler dimension. Okay, why is that? Very briefly, here we have a polystable vector bundle of slope 0. For each f is someday fi, now fi is stable of slope 0, so h naught is less or equal to 1. If it's 1, it's just a trivial bundle. So this implies that the rank of f is bounded by, h naught of f is bounded by the rank. Right. Now you can do the same for the symmetric powers. They are still stable. This implies that h naught of SPF is less than the binomial coefficient, which should be something like that, I guess, which is of the order of p to the r minus 1, constant times p to the r minus 1. Now this is enough. Oh, okay, this is enough to bound. Sorry, I forgot to say that because of the slope conditions here, we prove, I mean, it's not completely trivial, but we prove that h naught, this is in fact h naught of SPTX. Because of the negativity of G, the only sections which appear are those SPTX. And this is enough to show that the Kähler dimension, the Ithaka dimension of O of 1, or PT star x of 1, is less than this exponent r minus 1. And then this shows that the inequality here. And let me finish with second part, which is sort of nice. In fact, we have something more, which is due to the people working in, with foliations, Pereira, Touzé, and I think that's it. Moreover, we know that the determinant of f is torsion. We can, as I said, we can make our proposition is stable under étale covering. So by taking an étale covering, may assume then since determinant f is trivial, this means that the determinant of G is k minus 1, and so determinant of G star is kx. Now, the determinant of G star goes into the dual, goes into T star x, which is omega 1, and we take the n minus r wedge product, so we have this inclusions. And then a famous theorem of Bogomolov tells us that the algebraic dimension of X is less than equal to n minus r, which is the inequality I wanted here. Okay, thank you for your attention.